Okie dokie, friends. Lesson 5 in Unit 4 deals with Part 2 of what we call the Fundamental Theorem of Calculus. This will be the last video lesson on the Fundamental Theorem of Calculus because tomorrow is just a giant, well, tomorrow, Lesson 6, will be a giant practice day on Fundamental Theorem of Calculus, where we'll just run a whole slew of practice problems because that's just, we need it. We just need it. So in today's part, we deal with the Fundamental Theorem of Calculus, Part 2. And this is the part with which we are more familiar as calculus people, because this is the part that helps us actually evaluate integrals. This is the part where we actually say, okay, I want to find the value of this definite integral. How do I use that using antiderivatives? So here's the way the theorem reads. And I know you're doing two things at once. If little f is continuous at every point of the closed interval AB, and if capital F is any, if capital F is any antiderivative of little f on AB, then the integral from a to b of f of x dx is capital F evaluated at b minus capital F evaluated at a. This is the part with which you are much, much more familiar. Much, much more familiar. Little f has to be continuous because it has to be integrable. And capital F is any antiderivative. Because as we learned in our last lesson, all antiderivatives basically look the same except for a vertical shift. So the integral, the definite integral of little f of x from a to b is capital F of b minus capital F of a. There are two major consequences of this part of the theorem. One, any definite integral can be calculated as long as an antiderivative can be found. Any definite integral can be calculated as long as an antiderivative can be found. Two, there's an easy recipe for definite integrals. The easy recipe, you just take any antiderivative, substitute, substitute, and subtract, and you're done. You're done. So how's that look? Well, it looks like this. I want to evaluate the definite integral from -2 to 3 of 3x squared plus 4x dx. 3x squared plus 4x dx. And so I think to myself, all I need is an antiderivative of 3x squared plus 4x. Well, the antiderivative of 3x squared, that appears to be x cubed, because the power goes up by 1, divide by the power, 3's cancel. And the antiderivative of 4x, that's 2x squared. That's pretty true. So now all I have to do, and this notation just means I'm going to evaluate between -2 and 3, which means I'm going to substitute 3. I'm going to substitute -2 and subtract the answers. So what's that? 27 plus 18 minus, oh, this has got to be negative 8, minus 8. So those go away, 45. Every definite integral with an antiderivative in play will be evaluated exactly like this. Every one. Every one. So find the area between y equals x squared minus 4 and the x-axis on 0 to 3. That's this. Oh, lower. Here's x squared minus 4. Cuts the axis at 2. Here's 3. I need this area and this area. Now, you and I both know that this reddish bluish area is below the x-axis, so the integral value there will be negative. So I can't just say integral 0 to 3 of x squared minus 4 dx. I can't do that because if I do, then some of the negative area is going to cancel out with some of the positive area, and I'm going to get a not true number when it comes to area. Area, everybody goes positive. Everybody does. So what I need is the opposite of the integral from 0 to 2 of x squared minus 4 dx plus the integral from 2 to 3 of x squared minus 4 dx. And I can crank those out one at a time. Again, antiderivative, 1/3 x cubed minus 4x from 0 to 2, 1/3 x cubed minus 4x from 2 to 3. So I take the opposite of what happens when I plug in 2, and then I add plug in 3, plug in 2, and subtract. So what does that give me? That gives me an 8 minus an 8/3 on the front end. It gives me 27/3 is 9 minus 12 minus another 8/3 plus another 8. And so that's, what is that? Goodness sakes. 8, 16, 25, 13. 13 minus 16/3 is 23/3. As a side note, if you have a calculator handy, you can also do this problem on your calculator with some ease. Let's just bring that picture in. If I were to have, some function integral, I would simply integrate the absolute value of my function from 0 to 3. And I'd get the same answer. I would take the absolute value, because what does the absolute value do? The absolute value kicks all that negative area and turns it around positive. So if I integrate the absolute value of my function, then I get the actual area between my function and the x-axis. Does that almost make sense? Gosh, I hope so. Gosh, I hope so. Okay, so how is this going to pop up? Consider f of t. And f of t is this graph right here. 2, 4, 6, 8. You suck. I'm great. Oh, that's not what I want. Let's make it red. So that hits at 1, and then it maxes out at 3, and then it goes through 4, bottoms out at 6, comes back up to 8. We're going to let h of x be the integral from 1 to x of f of t dt. So in other words, h of x is that capital F that we've been building. And I want to answer some questions like, what is h of 1? Is h of 0 positive or negative? Where is h maximum? Where is h minimum? And then where are h's inflection points? Those are things I'd like to consider. I'd like to consider what h of 1 is h of 0 positive or negative, where is h a maximum, where is h a minimum, and where are h's inflection points. So if you're watching and you're like, I want to try this, hit the pause button and try it. I'll give it a go. h of 1. h of 1 is the integral from 1 to 1. The integral from 1 to 1 of pretty much anything is 0. That is completely disconnected from the fact that f of 1 appears to be 0. There is no connection there at all. I'm not even being sarcastic. There is no connection at all. Integral value from 1 to 1 of anything is 0. If the red graph was way up here, we'd still be h of 1 equal to 0. Is h of 0 positive or negative? Well, h of 0 is the integral from 1 to 0 of f of t dt. So the integral from 0 to 1 appears to be positive, and so we read it backwards. Are you 2 for 2? I hope so. Where is h a max? H is a max where f prime goes from positive to negative. Well, what's h prime? H prime is f. F has to change from positive to negative. I'm in a small space. You would actually write out F changes from positive to negative. You would actually write that out. I'm in a small space. Don't copy what I wrote. Copy what I said. That happens at x equals 4. Where is h a minimum? H would be a minimum where h prime changes from negative to positive. Well, that's f changing from negative to positive. F never changes from negative to positive. So h is either going to be a min at x equals 0, or it's going to be a min at x equals 8, because there are no mins in between 0 and 8. So the question is all of this area less than all of that area? And it appears not. It appears that the so-called negative area eats up all of the positive area, and so I would argue convincingly that it has to happen at x equals 8. And then where are h's inflection points? H's inflection points are places where h double prime changes sign, but h double prime is just f prime. So where does f prime change sign? That's where f changes from increasing to decreasing or decreasing to increasing, and that happens at x equals 1, at x equals 3, and at x equals 6. Those are your 3 inflection points. I hope you enjoyed Fundamental Theorem Part 2. Practice next time.